All right, looks like we're live. And I'm resuming where I left off yesterday. Yeah, so I have been going through so in order to learn Rust, in order to learn entity component systems, in order to make a roguelike, I'm going through this tutorial on bfknightley-productions.com, and we're on chapter 2 now. I've gotten the basics working, being able to put entities on the screen, defining their foreground and background colors, and what character they're being used, what character is being used to represent them. And if I can get into my working folder, we can take a look at the code that's actually doing all of this. We have a component in our entity component system called position. We've got a component in our entity component system called renderable. We have a struct called state, which only contains world right now, but I imagine it's going to grow. Otherwise, why create a struct for it? And then we have a tick method inside our state, which is implementing this game state trait. In that, we grab a list of all of the positions and renderables from the world. ECS is our world. So we go self ECS read storage to read the positions that are available as components and renderables that are available as components. And then using the magic of this join method on the tuple here of reference to position, reference to renderables, we get a position and a renderable for every entity that's in the system. This is our main. We're creating this simple 80 by 50 RLTK. RLTK is Roguelike Toolkit. So it's creating this simple thing. And here's our title, Roguelike Tutorial, although it's not showing up here. Roguelike Tutorial. Because I'm running this off a web page, because I'm building this with WASM and BindGen. So I can run it as part of a web page. It could also be run standalone, just as a compiled executable, but I'm doing it in web page because that's the way I want my roguelike to end up eventually anyway. So there we go. So in order for the world to understand what components there are, you've got these two components up here, right? Position and renderable. We have to register them with the world, ecs.register. And then in order to put entities in the world, we call create entity. We give them components with the with method. And then we call build to tell the create entity struct that we're done adding all of our components, and we just put it in the world. So we do this for the player, and we create a little @ sign for the player, and that's showing up here in yellow and black. And then we loop over 10 times, 0 through 9. We get a position and renderable for... we create a position renderable component for each of these entities, and we put this little smiley face in there. And those are red and black, and so there they are. And this is what we're up to in this tutorial. And here's all the code. I've typed this in myself. It's pretty close to what they've got here because I've been following along with what's above. So like they say, do this, so I type it in there. And the reason I type it in instead of just doing copy-paste is that way I actually get a little more understanding of how the code's put together. If I just copy and paste everything and say, yeah, it works, I don't feel like I'm learning anything. And they see, here's what the window looks like. And it looks almost exactly like ours, except it's in a browser instead of in its own standalone window. So now we're looking at random movement at this next phase here. And I figured what I can do just to keep things nice and clean, we do have a Git repo, and it's all, We don't want WASM. Actually, we do want WASM index.html. We don't want the other WASM. So maybe at some point, because the index is part of it, but these two are generated. So maybe at some point I'll have an index in like a separate source directory, and then we'll create a build script which just puts all these things here to run it. But for now, let's modify the get ignore to ignore wasm/rt star. So if I look at get status now, we do have our main. I think this is it. Yeah, brand new roguelike. So we're gonna just git add dot, which you always should do, right? Get status. It just has those, and git commit -m creating components and entities to go with them. There we are. Okay, so next up is this chapter. I think we're going to go to the end of this chapter and then call it a stream, because I don't stream long. My longest stream, I think, was a half hour. So random movement. This example showed you how an ECS can get a disparate bag of entities to render, right? Go ahead and play around with the entity creation. You can do a lot with this. Unfortunately, it's pretty boring. Nothing is moving. Let's rectify that a bit and make a shooting gallery type look. So we'll create a new component called left mover. Okay, let's do that. Source main. Create a new component. And call it left mover. And it doesn't have anything in it yet. We'll tell the ECS to use the type, so we register it. That's down here. Left mover. Okay. Now let's only make the red smiley faces left movers. So their definition grows to. So we have create entity for them, right? We give them a position, I times 7, y 20, renderable, boom, boom, boom. And now we're going to add a new component to this entity. So I guess this should go down here. And we'll just say, oh, I thought I fixed that. With left mover. And I guess we're just creating the empty struct to just tag it as a left mover. Notice how we've added one line with left mover. That's all it takes to add one more component to these entities and not the yellow @ sign. Okay. Now let's actually make the move. We're going to define our first system. Systems are a way to contain entity component logic together and have them run independently. There's lots of flexibility available, but we're going to keep it simple. Here's everything required for our left walker system. So we have a left mover component and a left walker system. So let's put that, put it above our main, I guess. So left walker system. Struct left walker. Impl tick A system tick A for left walker. And now we're creating the system data struct. So we did that. We did not do that before. This is new, something called system data. All right. Type system data. So the way Rust works is system is a trait and left walker is what we're adding the trait to. And when you have a type like this inside the impl block, it means that the system is tied to a specific type. And we're defining what that type is. So read storage with tick A and left mover, okay. And write storage decay, and position. All right, so left mover and position. So we're defining the system, the data for this system, this left walker system, is reading left movers and writing to position. That makes sense. If we're trying to make a move, right, we're going to be updating the position. So fn run mut self lefty mut pause self system data. All right, so do we understand this? So we're creating a function. We're implementing the traits function, mutable self, and then it's passing in a tuple. Oh, we're deconstructing the system data tuple into lefty, and lefty, I guess, is the left mover entity, or is the left mover component, and position. Okay. For underbar lefty pause. Okay. So we're not actually using that in lefty pause.join. Now here's the magic of join again. We have two storages that we are joining over, and as we find all the entities that contain both a left mover and a position, we're going to be putting them in here, or Rust will be putting them in there as part of the join iterator, as part of the iterator that join returns. Pause.x minus equals 1, and if pause.x is less than 0, pause.x is equal to 79. Okay. And once again, somehow we ended up being, indented too far. There, that's better. All right, so we're just subtracting 1 from the x position, and then if it hits 0, we wrap around to the end of the screen, because the screen is an 80 by 50 screen by default. This isn't as nice, simple as I'd like, but it does make sense when you understand it. Okay, I'm glad things make sense when I understand them. That's important. Let's go through it a piece at a time. Can I edit this? I want to edit this. I want to put the apostrophe where it belongs. Struct left walker defines an empty structure, right? Got that. Somewhere to attach the logic. So that's something that's making the system happen. Impl tick A system A for left walker means we're implementing spec system trait. So again, this is specs. We talked about that briefly last time, but maybe I should be looking at specs too to understand what's going on there. We're implementing the spec system trait for the left walker structure. Tick A is lifetime, right? I understand about lifetimes. Type system data is defining the type. Yep, I understand that part. fn run is the actual trait implementation required by impl system. The for loop is the system shorthand for the same iteration we did in the rendering system. Right? It will run once for each entity that has both a left mover and a position. Note that we're putting an underscore before left mover variable name. We never actually use it, right? So that way Rust won't complain. If we put this in here, if we don't put an underbar, then Rust is going to complain about compiling. Let me actually see if it'll build. Target, yeah. So that built very fast, 0.46 seconds. If I take out the underbar and try again, now it complains that we're not using it, and it says prefix it with the underscore lefty. So the meat of the loop is very simple. We subtract 1 for the position, and if it's less than 0, we scoot back to the right of the screen. We go back to the right of the screen. Okay. Notice it's very similar to how we wrote the rendering code. Yep. But instead of calling into the ECS is calling into our function system. It can be a tough judgment call on which to use. If your system just needs data from ECS, then the system is the right place to put it. If it also needs access to other parts of your program, it probably is better implemented on the outside calling in. Okay, I guess we'll understand that a little bit better as we go on. Now we've written our system. We need to be able to use it. So we add a run system function to our state. Okay? So going along with... Oh, we're just putting a run systems on state. We're not making it part of this. Okay. Impl state. Run systems. Mut self. Let mut LW equals left walker. So we're creating a new object of type left walker, which is our system. And then we say LW run now self.ecs. So so this system has a run now function on it that's going to call our run, and we have to tell run now which world to use right up here. Okay, that makes sense. And then self.ecs.maintain. I don't know what that does, but I think we're going to learn very quickly. This is relatively straightforward. Impl state means we would like to implement functionality for state. Run systems means we're defining a function that needs to be mutable. It's allowed to change things. Access to self. This means it can access the data. Yep. Let mut LW equals left walker makes a new instance of the left walker system, and run now tells the system to run and tells it how to find the ECS. So I haven't defined run now, so I'm assuming that the fact that we implemented a system for the left walker means it gets run now somehow. Although they're not explaining how that works. I don't know how that works. I'll have to look that up. Self ECS maintain tells specs that if any changes were queued up by the systems, they should apply to the world now. All right, there's specs rearing its head again. So we got to learn that system, or learn that crate. Finally, we actually want to run our systems. In the tick function, we add self-run systems. Okay? Do we do that before or after we do the render? I'm going to assume we do it first. It makes sense to do the update first, right? And then clear the screen and draw all our renderables. Nice thing is that this will run all the systems we register into our dispatcher, so as we add more, we don't have to worry about calling them or even calling them in the right order. Interesting. How would it know what the right order is? You still sometimes need more access than the dispatcher has. Our renderer isn't a system because it needs the context from RLTK. We'll improve that in a future chapter. All right. So should I be able to run? This is what your code should look like. Hopefully everything that we typed in works. If I run it with cargo run, the red smiley faces will zoom to the left. All right. So right now the red smiley faces are stationary. Let's see if this builds. And then bind gens. And then refresh. Oh, look at that. It worked. First try. That's a sight to see. Okay, this is a little jankier here, but I guess maybe it's a GIF or something. Moving the player. All right, let's save that. Get status. All right, cargo format. Get diff. What we got? Yep. Oh yeah, it cleaned this up a little bit for me. Appreciate that. Thanks. What about Clippy? What does Clippy tell us? Oops. I guess we'll have to wait for 165 things to compile. And looks like it all worked. No complaints. Right? Good. So it's just that. Git add source. Git commit left movers are now moving left. Okay, so now let's move the player. Finally, let's make the @ move with the keyboard controls so we know which entity is the player. We'll make a new tag component. Is that the first time they use that terminology, tag component? Yes. It's used twice in here. Oh no. I must have glossed right over that one. I read it earlier 20 minutes ago. All right. Moving the player. So we're going to create a new component. Let's put them here. Derive component. Oh, and they also have debug in there. I guess we'll be printing out the player. Let's register them. Okay. And then we'll add it to the player's entity. So we're creating an entity and we're telling the entity component system this guy is the player. And now we implement a new function, try move player. I guess we'll find out why it's a try move player later. Oh, and here's where we actually are going to start using this max min and the virtual key codes, right? I see the virtual key codes coming in and out in there. So let's add those back in. And then we're just going to implement a new function that just sort of hangs out, not attached to a state or anything like that. Try move player. Delta X is I32, delta Y, I32, and our ECS is the world. And it returns nothing. Okay. So we're doing the same thing we did for the renderer, where we grab positions and renderables, right? That's what we did up here in our tick function. But now what we're doing is grabbing positions and players. Okay, and there's only one player right now. Right storage. Position. And ECS right storage player. All right. And then we're going to do the join for and then underscore player pause in mut players, mut positions join, and we're going to update our X position at 79, max 0, pause X plus delta X. Pause Y is min 49, max of 0, pause Y, delta Y. All right, so we're updating the positions, but we're relying on our tick here. And this method is the method that actually redraws things, and I don't know how often that runs. Oh, there we go. And then, drawing on our previous experience, we can see this gains right access to the player in position. Yep, right storage, and joins the two, ensuring that it will only work on entities that have both the component types. Adds delta X and delta Y to Y, and does some checks to make sure you haven't tried to leave the screen. Why is it asking for right storage on the player, though? Okay, we'll come back to that. Well, a second function to read the keyboard information provided by RLTK. Okay. So another function that's just sort of hanging out. FN player input. game state is a state, and the context is RLTK match CTX key. Who calls this though? None. And sum key match key. Probably can simplify this with a let, an if let, right? Virtual key code left. Try move player -1 0 GS ECS. And we'll do the same thing right up and down. Right? And then default, do nothing. We ignore all other keys. So right, up, down. And then try move player 1. And then both of these get zeros. This is -1. This is 0 and 1. Okay. All right. So then again, we're learning about option types, which I'm familiar with. The context provides the key variable, which is, it's an enumeration. So a variable contain a value from a set of predefined values. Oh, okay. Yeah. It's a virtual key code. Right. And this is just extracting that. And now I'm going to try changing that to an if let and see if that works. That should work just as well. So, oh, now we have to add it to the tick. Okay, so that's how player input gets called, is every tick. Player input self CTX. So RLTK grabs the key codes, and then every tick we grab them out of the CTX. Okay, that makes sense. And it looks like that guy's moving around. Let's see if this builds. Oops. Unused import. Oh, I messed up. Okay. None. Arrow. There we go. And then bindgen. And then refresh. And now can I use? I can. Look at that. I can walk around. Isn't that exciting? And I can't. Oh, no, I can't go off the top of the screen because of that min-max function. I can't go left. And I can stand right in the way of all the monsters. Very cool. All right. So now I want to change that back to an. Well, let's check this in. And now I want to see if I can change it to an if let. All right, these are all the changes I just did. Added those back in. Added the player component every tick. We got the two new functions. We registered the player and we made that entity a player. Cargo format. Clippy it. It likes it. So get status. Get. Oops. Let's try that again. Yeah, it's better. Git add source. Git commit. Now the player can move using the arrow keys. All right. I'm going to now, because I do have 3 more minutes I can play around with here. I'm going to change this. Instead of saying match CTX key, it's interesting. It's going to come back with a none or a sum. And then once we have a none or a sum. So can we do it just that simply? If let sum key equals ctx key. Can we do it like that? And see if that builds. Yep. It's a semicolon instead. Try again. Liked it. Does it work? Find gen. I gotta put this in a script so I don't have to do this every time. Just create a simple build script. Refresh. Hey, look at that. Okay. Yeah, I think that's a little cleaner. Git diff cargo format. Yep, looks good. And this should come back clean. And it should just be that one file. Source git commit slightly cleaner code. All right. And that's the end of that chapter. Final code for chapter 2. And source code's online, but if I just download source code, I'm not going to learn. So that's why I am continuing to, oh, this is interesting. I can just run it from here. Let me try running that. And yeah. Oh, look at that. It works exactly the same as mine. Huh. So I must be doing something right. Thank you for watching.